Hey everybody, welcome to assignment 5 for CS302. And for this assignment, basically you're going to solve the same problem like in assignment 4, except now you're going to use your own custom hash map. So basically, the ideal is that when you create your own custom hash map and you verify that it works, in theory, you can just replace when you declare your unordered map objects in main and replace them with hash map instead. It should really work the same way. So it's important that in assignment 4, you use only the bracket operator for everything, for your search and find and insert, update, and so forth. So you don't have to do too many adjustments from assignment 4 main to assignment 5 main, because the hash map class we're implementing is much more basic than the unordered map class, because we don't want to really overcomplicate. We want to just focus on the data structure, not have to implement several methods, and we don't want to have to maybe use iterators and so forth, because this is already going to be enough work to just implement this custom hash map. Okay, so let's go ahead and now just talk about the hash map class. Okay, so here's your hash map header file. So of course we have our header guards as always. Here's your class hash map, and we have our T1, T2, our key and value type. Now let's look at the private members first. So we're going to have our struct node. So essentially this could have been a class, but I chose to use a struct. And each of these is going to be really going to contain one record in your hash map. So we notice we have our key and value pairs stored inside the node. And of course, you have a pointer to the next node in the linked list. So just to kind of first discuss this. So our hash map implementation is going to be kind of a modified open addressing. And it's going to take a little bit of separate chaining and open addressing, and it's going to hybrid those two together. So what we're doing is that, if you notice, if you recall in class, we have sort of a table that's going to be an array of linked lists. And for separate chaining, we can have a linked list contain multiple, if you have collisions, we just simply link up as many nodes as we want in that one linked list. And then for open addressing, we also have an array of linked lists, array of pointers, sorry, but each pointer, each element in your table, that reference can point to only one node, not an actual chain of nodes, or not going to be a linked list, but one single node. So the same idea will be here, except that we're going to kind of modify it. So in our implementation, we're going to have it where each element in our table, each index, so table index whatever I, is going to point to a linked list of at most 2 nodes. So you cannot have more than 2 nodes in each linked list, in each separate chain. So it's going to be kind of a modified form. So that's what we're doing. Now, I'm doing it like this because open addressing or separate chaining will be too simple to implement, because we covered it in class. There's also code available on that. So the purpose of this is to kind of get you to sort of using our techniques in class to try to figure out how to use this, how to implement this structure. So it's not really difficult. It's just a little bit different than the standard separate chaining and open addressing. Now, also to make things a bit more extra complexity, we're going to have 2 tables instead of 1. So again, it's not going to make things more complicated, but just a little different. So we have these 2 tables, and then we have these 2 items count. So we essentially, every time let's say in items 1 count, for example. So whenever we have an element in table 1, so table 1 at index I, if that gets maxed out, so if we have 2 nodes stored in some element in table, so table 1 index I contains 2 nodes, we then increment our items 1 count by 1, because now we max out one of our locations in our array of linked lists, or in our hash table. And same thing for items 2, it tracks how many elements in table 2 has 2 nodes in that spot, so it's maxed out. Then capacity, of course, will give us the capacity. So both table and table 2 will have the same capacities. So now let's go ahead and look at the rest of our functions. We have a resize function. We're going to resize by this amount, whatever's passed into the function. Copy map and deallocate map, these two functions will be used in your copy constructors and your assignment operators to sort of make life a little bit easier, I suppose. So you don't have to copy and paste, because your copy constructor and your assignment operator are going to be kind of similar to each other. So instead of copy and pasting code, you can write the copy map function. This function, essentially, you pass in a map object as a parameter, and you copy that into this map. You copy it into itself, basically. And deallocate map just deallocates the entire hash map. Now you have these two hash functions. I do give you descriptions of them in the PDF, but in this implementation file provided for you, I actually do give you these two functions for you. Now you may wonder what the heck is actually this part of the file. I will discuss that towards the end of this segment of the video, but I do give you these two hash functions. I do describe them in the PDF, but I'll give it to you as well to kind of simplify the work a little bit. So there we are. I do give you a couple of functions here and there. So I do give you the default constructor. This is going to assign items, and items 1, items 2 to both be 0. Capacity will be 5. We allocate our two arrays, and we initialize them to contain null pointer. So here's our assignment operator. We have to write that. This is going to be the bulk of your code, will be this operator bracket function. Here's your copy constructor, which I kind of give that to you. So copy constructor, we pass in a map object. So I actually set table 1, table 2 to both be null pointer. Well, actually, I may need to implement this actually in the implementation file, because I think you want to set items 1, items 2 to be 0, and then capacity to also be 0, and then we do our deep copy. Although we don't have to worry about that, because we're going to actually assign this map objects items 1, items 2 to this items 1, this items 2 anyways, so I guess it doesn't really matter, so that's okay. So here's the copy constructor given to you. We just simply initialize our table 1, table 2 to be null pointer to be safe, and then we just simply call the copy map function. We pass in our parameter. This function will copy everything in the map object into our self object, into the this object. And then I also give you the destructor. I also implement it for you. It's just simply just calls the allocate map. So you're going to have to write the assignment operator, which is going to be really just using essentially really the deallocate and the copy map functions. Resize will be a little bit tricky, but you actually can use the bracket operator within the resize function to make life a little bit easier. Then copy map, you have to write that. Deallocate map, you have to write that as well. So not many functions to write, really. And also, in theory, if your main file that you use for assignment 4 used only the bracket operator, then in theory, you should be able to replace unordered map with hash map. Everything should just work. So there's not a heck of a lot to write, really, in this assignment. So there's a description of all the contents in this, and there's of course the formulas for these for the hash functions. So now I want to, of course, next I'm going to go over this bracket operator function. It's going to be really the bulk of your work. I'm also going to use the OneNote to kind of draw out how things are going to work. So let's go ahead and now get started with the bracket operator function. Okay, so I guess I'm going to go ahead and just read this for you right here, if in case you can't read it yourself. Or actually, I'll just read it, but also kind of give you some more insight as to how this is going to work. And I do have an example prepared to explain this. So this bracket operator function is going to serve as both your insert and find. So you pass in a parameter, a key, and you want to find a node with a matching key. If you find it, return that node's value field, and you're done. Now, if let's say you can't find that key in your map, you determine that that key doesn't exist, you have to create a new node, link it into that correct linked list, and then return that blank node's value field. So that's sort of the idea. So here's kind of our method of how we're going to be able to search for our elements in our map. So first thing we do is we check our load factor. So if our table 1 or table 2 is 20% full, then we want to resize. So I'll cover resize in a bit more detail later. Let's not worry about that right now. So we will now compute index 1, index 2, and we're going to, of course, going to call the hash function 1, hash function 2. So index 1 equals hash function 1, you pass in the key, mod by capacity. Index 2 equals hash function 2, pass in the key parameter, mod by capacity. So you compute your two indices. Okay, that's not so bad. So then we check table 1, index 1. We check. If in that linked list you find a match, return that node's key. Oh, sorry, value field. Pretty basic. Now, if table 1 does not contain a matching key, so you have to search that linked list, it's not there, then what you're going to do is, well, you will now have to insert something into this table 1, index 1, if there's actual vacancy. So if let's say you have nothing there, so say table 1, index 1 is empty or only contains one node, well, then you can easily insert either to the front or to the back of that linked list. Now, if let's say we look at table 1 and we actually don't find our record, we don't find our element in table 1 at index 1, well then what we do is try the exact same procedure for table 2 at index 2. So we check that element, and it's also, we do the same exact procedure. We go through, we check that linked list and see if our key is there. If it's there, cool, return that node's value field. If it's not there, then we check. If there's only one node or there's 0 nodes in that linked list, then we can insert a new node into that linked list and then return that node's value field. Easy. Now, here comes step 6, where let's say we tried table 1, index 1, and there was nothing found there. Then we tried table 2, index 2, nothing was found there either. Then we had in both tables, we had a collision. So we have to use this method to update our update our index. So I, as always, will be your collision counter. So it's going to be initially set to, well, actually in this case, it's going to be set to 1 initially, because if it's 0, then index 1 gets reassigned to the same index like before. So we actually want to have I initially set to 1. And then we compute this. We take hash function 1 plus I times hash function 2. We compute that amount, and then we mod that by capacity. And the same thing, we also compute index 2. We take hash function 2 with that key plus I times hash function 1. We add these up, and then, of course, we mod it by capacity. And then using our new index 1, new index 2, we go back to step 3 and try the same thing over again. If we go through step 3, 4, and 5, and again, there is a collision, we have to increment our I count by 1, and then, recompute these two, and then so on and so forth until we finally find either the key or a vacancy. So that's the idea. So you can see it's a little bit of really linear it's not linear it's actually a double hashing technique, but it's, again, it's sort of a modified open addressing technique, so nothing too crazy there. So now let's go ahead and look at the example and try to visualize how this structure would look. Okay, and one last thing, I forgot to mention what these are right there for. This is basically just, since we're going to have a separate implementation file from our main and from our header, we have them all separated. And C++ templates don't like to really link very easily when you do G++, main.cpp, and then space hashmap.cpp. It doesn't like to link typically with templates. So putting these lines right here are going to tell us that in our main, we're going to have these type of hash map objects we can expect to see in our main. There's not a very good way of doing this, but I want to have our header files separated from our implementation files. So this setup is going to allow us to externally link our implementation file to our main. So that's why we have that there. So sorry if I forgot to mention that. Okay. So now let's go ahead and look at our structure here. So we have our two tables. Our key and values are going to be just kind of arbitrary for right now. We can see here that in table 1, we have one index where we maxed out our nodes, so items would be 1 in this case. And same thing for table 2. Index 1 we maxed out, we have 2 nodes right there, so items 2 contains 1. The rest are empty, and for table 1, index 3 has only 1 node in it, and table 2, index 4 has also just 1 node in it. So let's go ahead and look over how we would insert a new element in our table. So I'm not going to really go over actual specifics just to make it easier to discuss this setup. But let's go ahead and imagine we have an object of type hashmap, and we're going to pass in some string, and then we'll assign some value x to it. So internally, what we have to do is we have to compute our indices. So what we would do is we would have our index 1, and suppose we end up computing 0 for some reason. We computed 0. In index 2, let's just say for right now, we compute 1, just for the heck of it, to create this example. And our I, at the moment, this I is going to be 1 at the moment. So again, it's going to create a hypothetical situation. So now let's go ahead and go to index 0. And we create a pointer that points to the root node, or not root node, the head node of this linked list. And suppose our str is not found here, and it's also not found there either. So we traverse these two nodes, no match, no match. Okay, great. So now we're going to have to try, we have a collision right here. We didn't find in either spot. So now we go to index 2 in table 2, which gives us 1. So we go ahead and look through this. And let's say we don't find a match there either. Well, then what we're going to have to do now is compute our new index. So index 1 is now going to be 0 plus 1 times 1. So index 1 now is going to be 1. Index 2 is going, well, actually, we don't want to reassign just yet. So you have to maybe be careful with this. You have to maybe not assign just yet. So I'll just kind of have a temporary variable right here actually first. Maybe have a temporary variable there, just 1 for a second. Index 2 would be actually 1 times 1, so 1 plus 1 times 0. So it's going to be reassigned to the value of 1. This now becomes 1. So this is a pretty bad example, but anyway, we'll just try this out. So I guess the issue would be if index 1 and 2 are both to be 0, that would be probably a potential hazard, but in the examples I provided for you, or in main and so forth, everything does run. So I guess we're lucky, but this is actually relatively maybe not the best method of rehashing actually, but I guess it doesn't cause any issue. So we get index 1, and we find a vacancy there. So as a null, we insert a new node right here, assign the key to whatever that parameter was. We want to assign the value to t2 parentheses, just like discussed in class, then return that value field back to main. And of course, back in main, we can either overwrite the value field like this, or we can read the value field. So that's pretty much it. And the same idea over here. Let's suppose we do another insertion. Let's just do one more for right now. This str2 equals say x. So in this case right here, suppose we compute 3 for index. So let's say index 1 will be 3. We compute 3 for some reason. Index 1. Index 2, let's say we compute 4. So we go to index 3 of table 1, and suppose this first element right here, there is no match, and after this it's going to be a null. So we have to find a way to determine that this is only a one node linked list. So since it's not here, we can safely add a new node to the front or back of this linked list. So we add a new node into this linked list right here, and then what we do is now by adding this node, we can see that this is going to now maximize this linked list right there. Because now we had only one, now we put a second one, now it's maxed out, so we have to increment our items count, items 1, by 1 to make it now 2. So you have 2 elements in our table that are now maxed out. So that's sort of the idea for how we maintain our items count, essentially. Now, if I inserted somewhere in 1, 2, or 4, it would not cause items 1 to increase. Only if I insert into this location right here. And also double check, whenever you do look at a linked list, if it already has 2 nodes and it was no match, you don't want to insert there. Then you want to try the second table and do the same exact procedure like that. So that's kind of like the overview of how this setup would have to be done. So let's go ahead now and just talk a little bit about the resize function briefly. Okay, so for resizing, what you would do, I mean, there's many ways you can approach this, but the ultimate result is, let's say if you double the size of these 2 tables, so the capacity would then be 10. You create 2 tables that are both 10 elements, 0 through 9, 0 through 9, and then one by one, you have to go through every element in table 1 that's not vacant, and you have to insert that into this new table. And you can't just literally, allocate 5 elements and just deep copy it 1-to-1, because remember, when we have a different capacity, then we take our hash function modded by different capacity, each key may potentially map to a different index of the larger table 1 and of course a larger table 2. So when you have your 2 larger tables, you have them allocated, and you go one by one, you go through each of these 2 tables, and for every record that's not blank, you have to map it to the correct index of your larger tables. That's basically the idea of these. Now, the only issue is, well, you could of course can copy and paste code. You have to kind of use the logic in the bracket operator to complete this task. So you can copy and paste that code, or another way you can do this is find a way to using that star this. I remember what this pointer means, and star this is your self object. You can call the star this object, which is your own object, you can call its bracket operator, and you can simply make a call to that operator function within Resize. So what you could do is you could set 2 pointers, like a temporary pointer, one that points to table 1, and then the other that points to table 2. And then what you can do is allocate a new array to table 1 and table 2. So table 1, table 2 pointers would point to the new larger arrays, and then the temporary variables would point to the old original table 1, table 2. And then of course, since you modified the instance variable table 1 to point to a new array, same for table 2, you can use the star this object's bracket operator to simply just call the operator function. But you can of course copy and paste it as well. But the idea is that you create 2 larger tables, you have to one by one rehash them to the new locations, and make sure at the end of the day, table 1 and table 2 are assigned now to the 2 new larger tables. So that's sort of the idea for how the resize function would work. So again, I could have drawn some more stuff out for you, but I kind of want you to try to think about and of course figure it out. Now, if you're having a hard time with Resize, what you can do to test out your code is you can just simply in your constructor, or what you can do for the header file provided, you can of course go to the header file, which has a constructor implemented, and set the capacity to a large amount. Just to see, so when you're running your main program, if you make a really big capacity, then Resize will never be called because your table would never get 20% full. If let's say you have like 1 million capacity, and then you can test to make sure if your main program is working correctly. And then of course, if you set the capacity back to 5 and then it suddenly breaks, that means, okay, then you know that the resize function was the problem. So you can of course just make sure that the resize is the issue, and not so you want to make sure you can isolate the problem. So you run your main, you want to make sure that it's not the resize, or you want to make sure that the operator function is working correctly before you try to involve the resize. So you can just set the capacity to a big amount. If it works on that, your main, then try to set the capacity to a smaller amount and then see if the resize is correctly working. So anyway, let's go ahead and now just go over a test run of the program, and then that would be it for the video. Okay, so using the hashmap.h file provided to you, and of course you don't have to submit that to CodeGrade because on CodeGrade it already will have the hashmap.h provided there, but of course you can modify a header file, for the capacities and stuff. So you have your hashmap.cpp file, and here's one of your tests. So it's a very simple one. It's not gonna involve a resize, I don't think. So we just simply create a hashmap object, a string to an int. So you remember in the hashmap.cpp file, I actually do define an object in that at the very end of that hashmap.cpp file that contains this. That way, it'll be able to link the implementation file to this main. And of course, our deep copy test, this one just simply creates a few hash maps. We call it copy constructor. So here we want to copy h1 into h2 deep copy. And then over here, we copy everything from h2 to h3 using assignment operator. So that's just a deep copy. They're just a very simple, it's not anything insane. There's no rehashing, just you one by one, you allocate the amount of space. So for example, like h1, you allocate the same size for h2, allocate h2's table 1, table 2, and then 1-to-1 just copy everything from h1 to h2 literally 1-to-1 linearly. So nothing fancy there. This one, I think I used a little bit of Nickelodeon characters here. But this one was an example where we did a lot of insertions, and this I think does cause a resize to happen. So then we want to make sure after resize we don't lose any of our records. At the very end we just output them. So just simply test out that content. So to compile this, if I want to test out the basic map test, just G++, basic map test, and then hash map.cpp. So we can link the two files. You can link our main with our hash map. Now, if I didn't include those template definitions in the very end of the hash map.cpp file, we would not be able to link a template class to a main externally like this. So that's kind of why we did that. So you can sort of have that same setup like we did in CS2. Now to run, as always, a.out. That's the output you should get. Now to run the other mains, you would just do deep copy test.cpp hash map.cpp, and there we are. So that's the output that you would get. So sorry, wrong file. So it's going to be in the deep copy test. Okay, I was confused. Anyway, there we are. So everything should just be the way it is. So there's that. And now, of course, for the last one, we have the resize test.cpp hash map.cpp. And you should get this output. So that's going to be also tested on CodeGrade. So a very simple test to make sure your hash map is just simply working. This one checks the deep copying and the deep copying. This one tests out to make sure the resize function doesn't cause any of the records to be lost. Then, of course, for the main, same main I used in assignment 4. And to run it, a.out. I pass in input 0, 1. Sorry about the background noise there. The txt. There we are. And for 0, 2, there we are. 0, 3. Should be the same output that we had from assignment 4. So anyway, that's the end of the video. So I hope this gave you a little bit of an idea to get started on the assignments. So I guess that's it for now. So until next time, and happy coding.